Here are the solutions to all the problems I assigned on Friday, also including problems 5 and 13 from the assignment from Thursday. So I went over 1 and 11 in Friday's video. Now let's take a look at number 3. This is off of pages 380 to 381. What's a little different about this, and I'm actually going to talk about this within this problem, but that's also going to be part of today's new lesson. There's a couple ways that we could always set this up. So if you notice, these equations are solved for x in terms of y. So I'm going to come back to that as a second way to do this problem. But for right now, in order to write the area or the integral to help us find the area as the top curve minus the bottom curve, we want to solve for x in terms of y. So if we take x is equal to y cubed, that just means y is going to be the cubed root of x, or x to the 1/3. And then if we take x is equal to y squared, notice it's just the top half of a sideways parabola. So when we go to take the square root here, we just use the positive. So y is going to equal the square root of x, or x to the 1/2. So the area here to calculate, the integral here rather, to calculate the area, we're going from 0 to 1. I already show the points of intersection. Top curve is going to be the cubed root of x, so we'll have x to the 1/3. Minus the bottom curve is y equals x to the 1/2 dx. As we carefully take the antiderivative here, if we add 3/3 to 1/3, we're going to get 4/3, and then we multiply by the reciprocal. Minus, we'll have x to the 3/2 times 2/3, and we'll evaluate that from 0 to 1. So if we substitute the 1 in here, we're just going to get 3/4 minus 2/3, and then we would get a minus 0. So this would give us 9/12 minus 8/12, so our area is 1/12 square unit. Now what if we left this? We could also do this with respect to y, and that's going to be the new part today. So we could have left it like this. Now the idea here is, and I'm going to do this just to kind of show a point here. When we're dealing with respect to x, we take the top curve minus the bottom curve. When we deal with respect to y, we're going along the y-axis. So imagine if we were to rotate this, it's still going to be the top curve minus the bottom curve, but in this case, if we take it back to its original orientation, that becomes the rightmost curve minus the leftmost curve, and we're going again along the y-axis. So if we did this with respect to y, we would have our area is the integral from this 0 to 1. So the integral is y goes from 0 to y equals 1. The rightmost curve is going to become y squared. The leftmost curve is going to be y cubed, and then we do dy. So now this will become y cubed over 3 minus y to the 4th over 4 from 0 to 1. And we'll get 1/3 minus 1/4, and then minus 0. So this will give us 4/12 minus 3/12, which is also 1/12 square units. Pretty neat. So multiple ways we could do this with respect to x, with respect to y. Now this one wasn't too terrible to solve for y in terms of x, but others are going to be a little more involved. But like I said, in today's lesson, I'll go over a couple more examples where we do this. All right, so next we're looking at number 5. So if we notice, this top curve here is y equals 2x squared, and then the bottom one is y equals x to the 4th minus 2x squared. So there's a couple ways we could set this up, but everything is still with respect to x. So we'll say the area. Now notice there's symmetry here. So we could set this up. We can go from -2 to 2. And again, our topmost curve would be the 2x squared. We just have to be careful as we subtract a binomial here. And then the lower curve would be the x to the 4th minus 2x squared. So that's one way to do this. Or if you like to work with zeros, that does make evaluating a lot quicker. we could separate this. We can go from -2 to 0 of 2x squared minus x to the fourth minus the quantity x to the fourth minus 2x squared dx plus the integral from 0 to 2 of the same function here. Or, and again, because there's symmetry, we could just go take the integral just from 0 to 2 and then just double it. And then we don't have to worry about working with -2 at all. So these are three equivalent ways to set this up. So because this third way seems to be the quickest, I'm going to go from here. So I'm going to start by carefully distributing this negative sign. So we get 2x squared minus x to the fourth plus 2x squared dx. Combine our like terms. So we're going to get 4x squared minus x to the fourth dx. Take the antiderivative here. So we're going to get 4x cubed over 3 or 4/3 x cubed minus x to the fifth over 5 from 0 to 2. So this will become 4 times h, so we'll get 32/3 minus 32/5 minus 0. And I'll leave you guys to figuring out the common denominators here and adjusting the numerators, but this leads to the final answer of 128/15 square units. All right, now for number 8, neither one of these are really, well, the first one's okay. Y is equal to x squared, that's good, but we want to take this, and you can already see that there was writing here. We want to solve this for x. We get x is equal to 2 minus y or negative y plus 2, and then we're good to go. However, what I was kind of pointing out in class the other day was right here when x is equal to 1, the top curve switches. So y equals x squared is our top curve here, but over here it's now that line. X is equal to 2 minus y. So we have to set up two different integrals. So the first is going to be the integral from 0 to 1. And since we're just going down to the x-axis here, we don't have to worry about subtracting anything. It's just going to be like subtracting a 0. So the first one's going to be 0 to 1 of x squared dx plus the integral from 1 to 2 of, and I should have solved for y. Y is going to equal 2 minus x. To make it easier. If not, we still could have done this and then just put a dy after it. We still would get the same thing. Alright, so as we go to calculate this, we're going to get x cubed over 3 from 0 to 1. And we'll get 2x minus x squared over 2 from 1 to 2. So here we're going to get 1/3. We'll get 4. Then we'll get 4 over 2, so minus 2. Then we have to subtract when this is 1, so we'll get 2, and then minus a 1/2. So this will give us 1/3. We'll get 4 minus 2 minus 2, so that's just going to be 0, and then we're going to get a plus 1/2. And 1/3 plus 1/2, that'll give us 2/6 plus 3/6, so we get 5/6 square units. Okay, so for the rest of these, I already have them worked out, but I'm just going to talk about the setup of them and any other key features about the problems that I want to make sure that you guys understand. All right, so for number 9, we definitely have two portions of the graph because we're always going to ask ourselves, at a point of intersection, do the graphs sort of flip? Or do they change what the top graph is compared to the bottom graph? And in this case, it does. So if you take a look, the top graph, as we go from x equals -2 to x equals 0, is the cubic function, and then the lower graph is going to be the quadratic function. So our first integral I know this was a lot to write out, but it's from -2 to 0. And carefully watch your subtraction signs. Anytime you have to subtract a binomial or larger, make sure you keep that in parentheses. So here we have the cubic function minus our quadratic function. Then, of course, put your dx. Plus, and then we go from the integral from 0 to 2. Now the top curve is the quadratic function. We have that first minus our cubic function. And then you can scroll through. Definitely simplify. Combine your like terms. So you can pause the video just to check your steps for number 9. Now in this case there was no symmetry. We always want to look for that. It will make our calculations by hand go by a lot quicker. Alright, now for 12, 13, and 14 we had to sketch the graphs. We also needed to find the x values of the point of intersection. So just showing you for number 12 I set the two functions equal to each other. So they intersect when x is equal to -1 and 3. So then over here I went ahead and graphed them. So in purple here, this is the area we need to find. So here's our two graphs. So we notice the entire time from x equals -1 to 3, the quadratic function is the top curve. So we just write that out minus our constant function, which is just -3. This one wasn't too terrible. Now there is symmetry here, but we don't. It's usually best to do the symmetry when a 0 is involved. I mean, you still could have. You could have just taken it from 1 over to 3 and then double that. And then you could check your work. Pause the video if you still need more time. Alright, for 13, again, we want to set these two equal to each other, or they're easy enough to graph. They have nice points of intersection here. So what's in green is the area we need to find. We definitely have some symmetry here, so that's what I used. This one did involve a 0, so we want to double the integral from 0 to 1. The top curve the entire time is the 7 minus 2x squared, and then carefully subtract the x squared plus 4 quantity. Alright, then for number 14, this quartic function was a little much to graph, but we could still find some nice points. There was a little bit of extra algebra work I did here, so I did set them equal to each other. We have 4 points of intersection at plus or minus 2 and at plus or minus 1. Now to help me graph the quartic function here, I found the x-intercepts of that, so that's what I'm going to show you next. Now remember, square root of 2 is approximately 1.414, so I just went almost to 1.5 here, so those are my x-intercepts. And the leading coefficient is positive, so this opens up. I also found the y-intercept, which was 4, so that's what allowed me to graph here in green. And then y equals x squared. I stretched out my x values along the x-axis, though. But we could still exploit the symmetry here. We can go from 0 to 1, the quartic function minus the quadratic, and then from 1 to 2, the quadratic minus the quartic. So I just set this one up. Combine your like terms, though. Notice for the first one, I had my quartic, which was a trinomial, just minus a monomial, so I didn't really need parentheses here. But over here, I definitely need to subtract every term. But you should be getting an 8 square units for that answer. And again, pause the video if you still need more time. All right, these next two problems came from section 7.1. This was the idea that if r of t is a rate of change, Then the integral from a to b of r of t dt is the total accumulated amount. So that's what we're looking at here. So in 21, this function here, c, this is the rate of consumption. Therefore, the total consumption, Tc, is the integral from 0 to 10, because it's just over 10 years, of this function here. Now, most of the time when it involves decimals, yes, you could just use your calculator. I went through, though. I still use the calculator to do some multiplying here, but I still just showed the steps. It's good to get practice here. We had to use U substitution. You could take a look at the integral steps. So the total consumption turns out to be almost 333 billion barrels. And 22 is very similar. Again, I worked it out by hand just so we could get practice, especially with U substitution and some trig functions as well. Here we're dealing with home electricity use. So here it has the average consumption rate is given to us as C of t. Then the average daily consumption, notice that's not a rate there, that's just how much is being consumed daily, would be the integral from 0 to 24 hours in a day of C of t dt. So we would write this out. And like I said, yes, typically something like this would be a calculator problem, but I still went through. So you could take a look at the steps, the U substitution that I started to use in this third step here. Remember, when we do that, we want to say, if we're using U, we have to go from t equals 0 to t equals 24. And what's nice with the cosine functions here, they actually cancel out, and we're just left with 93.6 kilowatt hours for the total daily consumption. So as always, guys, make sure you're going back to correct these. So let me know if you have any questions.